cutting anyways, Zoom.
Okay.
Yes.
Okay, cool. I hope that everybody is well. Today I'm presenting our paper, Generating Custom Set Theories with Non-Set Structured Objects, and hopefully explaining why we would want to do such a thing. My name is Kieran Dunn. This is joint work with Joe Wells and Firouz Kamaruddin at Heriot-Watt University in Scotland. So in the first part of our talk, I'm going to talk a bit about the role of sets in the foundations of mathematics. So when we talk about a foundation, we're talking of a small formal system that models the practice for mathematicians. Foundations, of course, must give us an explanation of common mathematical concepts and also a means for reasoning about them. Foundations are then implemented in computer software to help us write and verify proofs. And some theorem provers will emphasize the use of sets in their foundations, i.e. Isbell ZF, Mizar, MetaMath. And then other more popular provers will emphasize the use of types in their foundations, like Koch, Lee, Isbell Hull, and Agda. So in a formalism that emphasizes sets, we typically only have a few types, one for sets, one for truth values, and types for operators between those types. So for example, the empty set is of type set, power set maps from sets to sets, and the membership relation maps from sets to sets to truth values. And then when we work within one big type, we encode everything as type set. So natural numbers use the von Neumann encoding, ordered pairs use the Kuratowski encoding, and functions are then defined as sets of ordered pairs. And when we work within one big type, in this way, we have freedom to state things however we want, because we don't have to abide by any type discipline. However, the user ends up being on their own when they want to keep track of the intended meanings of all of these sets. What's a natural number? What's an ordered pair? What's a function? Where does this function map to? All of the stuff that a type system would keep track of. And also, when we have all of these different representations, it's actually possible that the sets that are being used to represent all of our different objects can actually overlap with each other, as we'll show now. So this can be demonstrated by this toy function g, which we might want to formalize, where g of x is equal to 0 if x is equal to the set of 1 and 2, and g of x is equal to 1 if x is the ordered pair of 0 and 1. And we can try to formalize this function as a set of ordered pairs, where the set of 1 and 2 maps to 0, the ordered pair maps to 1. But then due to the choice of our encodings, which we had before, these are actually represented by the same set. Therefore, we are contradicting the definition of function because we're trying to map the same input to two different outputs. So we can get around this by tagging our representations so that they're completely distinct, so that we don't have this overlap problem. So we could choose two tagging functions, tag 1 and tag 2, where tag 1 maps sets of natural numbers to some set B1, tag 2 maps pairs of natural numbers to some set B2, where tag 1 and tag 2 are injective, and B1, B2 are disjoint. And then we can redefine G so that we're acting on these tagged representations, where tag 1 always makes sure that something is meant to be represented as a set. Tag 2 always makes sure that that thing is represented as an ordered pair. And then we can have well-defined results for G acting on these tagged representations. But what if we don't want to do this? Because generally working on tagged representations is quite ugly. It distracts us from the reasoning that we're actually trying to do. And it could be painful to automate in a automated theorem proving scenario as well. So we could use a type theory where we organize all of our objects into quite fine-grained types rather than one just huge type where we shove everything into. And then we use this type information to automate all of this tedious reasoning around tagging. And the type information can also be used to prevent users from performing syntax, which is mostly unwanted. However, when we're formalizing a piece of math and we have some math objects which aren't already within the system, we don't always know how to define a type for those objects. And a lot of work is done figuring out the right types for the right objects. And in some cases, having to obey all of the typing rules can get in the way of the reasoning that we're actually trying to do. So we asked the question, is it possible for us to have more flexibility? Is there a foundation in which all of our mathematical objects live within one big type? And when I say big, I mean the size of a set theory, where we have everything shoved in that. But have some of those objects in that type that are genuinely not sets. And our research is aiming to test whether this approach is workable. So the paper that I'm presenting right now shows how to generate axiomatizations and build models for set theories that have sets, of course, but also non-set ordered pairs, non-set natural numbers, a non-set exception object, which can be used for undefinedness, and it can't live inside any other object like a set or an ordered pair, and also axiomatizations and models for modular combinations of all of these different features, so we can kind of mix and match. So the next part of the talk will focus on the axiomatizations, and the last part will give a brief overview of how we do the model building. So part 2, how do we get these axiomatizations? So axiomatic set theories are traditionally just collections of first order or second order axioms, which will characterize a membership relation over a domain of sets. The most popular systems that people will know here are ZF and its variants like ZFC and Tarski-Grothendieck. The axioms of ZF will tell us when sets are equal, which sets must exist, that is the results of operations like union, power set, and replacement, that there is an infinite set, and that there are no infinitely descending chains of sets. A generalized set theory, and this is the term coined by Axel in 1996, is a theory that has pure sets, which are the sets that you'd find in ZF. So sets that contain sets containing sets, all the way down to the empty set. And these generalized set theories are distinguished from our typical set theories because they have non-set objects, which are things that do not contain anything via the membership relation, but are not equal to the empty set. And then, of course, we would want to mix and match our sets with non-set objects so that these non-set objects can actually be contained in sets. And such sets are called impure sets because they mix these things. And there have been many generalized set theories that have non-set objects, which are called elements or atoms, but these typically have no internal structure. So we use this terminology non-set object to avoid confusion between these kinds of elements, because we're going to use some non-set objects to, as we said before, to represent ordered pairs, natural numbers. So to actually get these generalized set theories, we combine what we call features. And this happens within a logical framework that's partially inspired by Isabelle Pure. And each feature consists of a signature of symbols for predicates and operators, a theory of formulas which specify those symbols, an ownership predicate that identifies the members of the feature, and a child predicate that relates a structured object with its children. And we'll give some examples of the different features that we define. And so far we have defined a set feature, a pair feature, a NAP feature, and an exception feature. And when we combine features, we have to generate some additional axioms along the way to basically stitch everything together. So we get a set of features, and then out comes a set of axioms for a generalized set theory that has those features. So the signature for the set feature has 9 symbols, including a membership relation, this ownership predicate set, which says yes or no if something's a set, and of course a power set operator, for example. The theory has 10 axioms, including one which characterizes this set predicate, this ownership predicate. It says that something is a set if and only if it's the empty set or it contains a member by the membership relation. Power set axiom, first given by Zmello, which says that every set has a power set which contains all of the subsets of that set. The child predicate is simply just the membership relation. We define the usual syntactic sugar for singleton and pair sets and so on. And an example of a formula we might prove from these axioms is, say, the pairing theorem, which says for any object B and C in the domain, we can make the set of B and C. And in some systems, of course, this is taken as an axiom, but in ours, it's just a theorem. The pair signature has 2 symbols, a pairing operator, which we have the usual syntactic sugar for, the ownership predicate pair, which says yes or no if something is a pair, a theory that has 2 axioms, one which characterizes a pair as something which is made by the pairing operator, the standard characteristic property of ordered pairs, first given by Piano, which characterizes what the meaning of the pairing operator, child predicate, which says that for a pair P and an object X, X is a child of P if it is one of that pair's projections, if it's either on the left or the right of that pair. An example of a formula we might prove here is if X is not equal to Y, then X and Y and X are two different pairs. Easy. The signature for the natural number feature has three symbols: 0, successor, this ownership predicate nat. The theory has 6 axioms, including these ownership axioms. Say 0 is a natural number, the successor of any natural number is a natural number. An induction axiom, which was first given by Dedekind, and this is a second order axiom. If we note that this is quantifying over properties P, and this axiom does not mention the concept of set. So this means we can use the nat feature independently to do something like piano arithmetic. But we can also use it with the set feature to then perhaps derive a set version of this induction axiom, which is seen in some formulations of piano arithmetic. Natural numbers have no child predicate. We don't consider these structured objects within our system. Syntactic sugar for the numerals 1, 2, 3, and so on. So to combine these features, we take a union of theories of the features. We add axioms that ensure that all objects are owned by exactly one feature. And we also have to add a well-foundedness axiom that uses these child predicates. And this is to ensure that there are no infinitely descending chains of sets, pairs, or mixtures of the like. So here's an example. We might want to define a theory ZF star that has the set, pair, and natural number features. So to do this, on the first line, we just combine the three theories: GZF for the set feature, P theory for the pair feature, N theory for the nat feature. And then the next two lines here are the axioms that make sure that all of the objects are owned by exactly one feature. And then the last axiom is just an abbreviation for our well-foundedness axiom. And it's kind of an axiom schema that's parameterized on the feature. It gets the child predicate and then stitches them all together in a way that generates the well-foundedness axiom. And the exception feature uses quite a more complicated combination process, still needs some debugging. We need to make it more uniform with our standard combination process, so it won't be shown here for now. So if we're working in a theory like ZF star, then we will have sets, pairs, and natural numbers as completely distinct objects, which means that we can redefine G, the function we were trying to define earlier, using these new objects that we have. And because we know that they're completely distinct, we have no representation overlap. We know this set is never equal, well, we know that any set is not equal to any pair. Therefore, G of the set of 1 and 2 and G of the pair of 0 and 1 are completely well defined. So in conclusion of part 2, the features allow us to specify mathematical objects independently of any representation. We can combine these features to generate axiomatizations of set theories in which the objects of those features are completely distinct. This provides us with a formal justification for the kinds of mathematics that would just assume that all of our sets, pairs, and natural numbers are completely distinct. And this is something which is usually assumed can just be done, and that ZF can be adapted to work in this way, but it's actually quite hard to find the formal details of how this is carried out. And this is one account of how this can be done. So in the future work, we would like to be able to develop a GST that has an abstract number system where we have naturals, integers, rationals, reals, possibly complex, such that they have this subset relation between them all, and they're completely abstract and obviously not sets. We would also like to have non-set functions, non-set ordinals, and non-set structures like groups and rings, etc. So in part 3, we're going to talk about how we build the models of our GSTs. So ZF is believed by nearly everybody to be consistent. That is, there is no formula phi such that ZF proves phi in its negation. And this is believed due to nearly a century of quite intense scrutiny of ZF's axioms. However, if we're adding extra axioms into our system and modifying some axioms, this could introduce contradictions. So how do we know that our GSTs are safe to use? So if we can build a structure in a consistent GST gamma 1 that satisfies the axioms of a GST gamma 2, then we know that gamma 2 is consistent. So to support this approach of arguing consistency, we develop a model building kit, which may be invoked within any generalized set theory with the set feature. And because our model building takes place within our generalized set theories of our framework, we're building our models at the object level rather than some model theory in the meta level. So we need to implement this requirement that each of our objects are owned by exactly one feature in order to model our generalized set theories, which have different features. So this means that the objects in our model are tagged in the way that we saw earlier with G, so that we can distinguish them within the model. And we currently build everything only using pure sets. So let this pairing operator be the Kuratowski encoding of ordered pairs, and let n star be the von Neumann natural number of n. So if we want to translate a set of ZF star into a model, we tag that thing with 0 in a Kuratowski ordered pair, and then recursively apply this transformation to the contents of that set. Same with ordered pairs, we tag it with 1, and then we convert that pair into a Kuratowski ordered pair and recursively apply the transformation to its contents. For natural numbers, we tag it with 2, and then just take the von Neumann natural number of that number. So then if we want to see this as an example for one of these ordered pairs, this one which uses a non-set ordered pair and non-set natural numbers, it becomes this bunch of nested ordered pairs within the model for ZF star. So we need to fit all of these objects that we have into one model of a set theory, but we need to do this within another set theory that's the same size. And in general, building a structure of this size is just quite problematic. And this is the same for building models of ZF as well. So a way to get around this is by building models as cumulative hierarchies of sets, and you do this via transfinite recursion over the ordinals. So we take this approach as well. So we have a transfinite recursion operator to define a model building operator, which does all of this tagging for us. So we don't need to define all of the tagging every single time. And then we can tweak the parameters of this model building operator to model all of the different features of our generalized set theories. So to understand how building a model in one GST can be argued for consistency, we first have to understand that we support two ways of presenting a generalized set theory. We can either directly assume a set of axioms or define a model and then work in that generalized set theory by proving that that model satisfies some axioms of another generalized set theory. So to support the second approach, our logical framework has many domain types, for each of which is one big type where we situate a generalized set theory. And therefore we have constants for each domain. So an empty set for domain 0, an empty set for domain 1, so on. And then therefore formulas that speak about each domain as well. So then we can build a model in one domain, domain I, and then we can actually connect it to another domain J to support the second approach here. So to do this, we use a technique that's used in HOL provers that allows us to present a portion of an existing type as a fresh abstract type. And this is done by forming an isomorphism using these abs and rep operators between the model in domain 1 and the entirety of domain 2. And then therefore the formulas that speak about the model in domain 1 have counterparts in domain 2, where the truth of these are preserved by the isomorphism of the abs rep. So to understand how this works formally, we can see an example of two different ways we might axiomatize two different GSTs, or present for that matter. So if we have gamma 1, which is a set of formulas specifying a generalized set theory in domain 1, and gamma 2 specifies a GST in domain 2, the direct axiomatization approach would say, take gamma 1 as axioms, reason in domain 1 with its deduction relation, take gamma 2 as axioms, reason about domain 2 with domain 2's deduction relation. And then, yeah, that's how we would do our reasoning of those two set theories. However, the indirect axiomatization approach says that we can take gamma 1 as axioms and reason with the deduction relation of domain 1, and then build a model using a model building kit of gamma 2 in domain 1, and then connect the model that's in domain 1 to domain 2, and then just prove that gamma 2 holds of this model, of the connected version of this model, and do all of our reasoning about domain 2 just using domain 1's deduction relation. So then this means that if gamma 1 is consistent and our connection mechanism is all safe, then we know that gamma 2 is consistent. So in conclusion, sometimes it's useful for us to do a lot of reasoning within one big type. But typical set theories will provide this approach, but having everything as a set is quite unsatisfactory. So the work that we've presented shows that we can define mathematical concepts independently using features, and then generate axiomatizations of set theories that have these features combined all into one big type. And our model building kit can then be used in any of our generalized set theories, and it can be used to, and so far we've used it to build models of generalized set theories that have any of the features that we've defined so far. And then the connection mechanism allows us to present a generalized set theory in terms of a model, which provides us for a method for showing the consistency of generalized set theories. In the future, we'd like to make the specification of GSTs a bit more user-friendly. So that could mean a kind of uniform process for specifying features and the models of those things. So perhaps finding a representation, proving some properties about them, and that being sufficient for a consistency argument. And also, it would be nice that users perhaps didn't need to be aware that they're always working in a different generalized set theory. It would be nice if we could define a feature and then simply just add it to the set theory that we're working in as fresh objects. And also, we're working on a computer implementation to verify our current results. And also hopefully automating the feature combination procedure, as this is just a simple algorithm. We'd like to automate the model building and connection process. We'd also like to be able to transfer theorems between generalized set theories that have common features between each other. And finally, we'd like to be able to have subtypes for the portions of the domain which are owned by each of the features. And that is everything. So thank you for your attention. If you have any questions, I'd be delighted to answer them. Cheers.
Thank you. I clap for everybody. So yes, there are questions. The first one is by Michael.
So if I understand this correctly, the model building method and kit is essentially moving stuff out of the non-sets types into kind of objects in the ZF, into the set type thing.
Sure.
Much more interesting, of course, and I would think of that as a lowering thing. Much more interesting, of course, is if you had a raising thing. Say you have done some work on Kuratowski pairs in set theory, and at some point somebody tells you, you know, there is this pair non-set thingamajig. And then you would just basically like to push a button and say, oh, move all of that over.
Yeah, for sure.
And since you're doing more types, this becomes more and more useful. And I would like to hear something about this from you.
Sure. So this isn't something which I figured out just yet, but it's something that we definitely want to support. So when I said at the end in the future work, kind of a uniform way of specifying features and models, it's kind of what I mean, like to be able to just specify the Kuratowski encoding and prove those properties about it, and then have the corresponding non-set version in a new GST, and then hopefully then transfer all of the theorems that you've proved about that across. So that would be nice. And I have an inkling of how that might be done. And I'm currently experimenting with the lifting and transfer packages in Isabelle. So I'm getting a bit of an intuition about how that stuff works, how you move theorems from kind of raw types to the more abstract versions. But this will obviously look a lot different in our context.
Thank you. Are there more questions?
No, but can I add a remark? I mean, that's a very good point, Michael, but I think what we have in mind is like, you know, you have like, if you think of like the cube of the type systems, you know, you have the simply type lambda calculus, you have the second order lambda calculus, you have the dependent type lambda calculus, you have the calculus constructions, and, you know, like they don't all meet. They are not all subset of each other. The calculus construction contains all the ones that is below it. And then you know how. So of course we want to construct the models and we want to construct the proofs so that they work, that we can carry out. Yeah. So there is a lot of generalization. First, I think the step of having like the basic Z set theory and then building any extra features you need on top of it by getting more and more generalized and then combining them. You're getting much more dimensions than the cube of Barendrecht of these type systems. But then of course, the idea also is to generalize the model building and the structure to see what is common to all of them and what. So there's a lot of work. I mean, Kiran is doing fantastic. This is a PhD project and he's doing fantastic on this, but the sky is the limit. That's what I believe. But another important thing, what he's doing is he's formalizing in a theorem prover. I mean, almost quite a lot of the proofs done on the paper are already formalized in Isabelle. And you know what that means to do the formalization of the entire difficult mathematical structure.
Can I add as well to my previous point? When we build a model, we have to prove that that the representation within the model satisfies the axioms of the generalized set theory. So in a sense, we are already doing this transfer of theorems about the representation to theorems about the abstract version. And if you wanted to have some extra properties across, then you can easily do that. But sometimes you want a small interface which you're moving over. And in the case, this is only 2 axioms for the pairs.
Thanks very much.
If I can get provocative a bit, you start with the depth basically, and you add features. And the features you showed us, the natural numbers, the pairs, and so on, are coming in a sense from type theory. So is your adding feature moving type theory on top of the depth or replacing the depth or?
Not necessarily, because I don't know, this is somewhat more, you're doing it all within one big type anyway. So you don't have to deal with all of the typing rules. Obviously, you still have to do this bookkeeping. You still have to keep track of what is a set and what is a pair in some way, but you have a bit more freedom about how you want to do that. You're not restricted to everything either being a set or going full on type theory. So it's perhaps somewhere in the middle, but yeah, it might turn out that way.
Claudio, you know how De Bruijn used to go everywhere in Europe trying to tell schools and teachers and universities, oh, set theory alone is not good for math. You really do need type theory. I mean, De Bruijn was a great advertiser of type theory, yeah? But here it's custom made. You build in your set theory the bits you need, because type theory, as Florian said, can be hard. That's it. Once you commit to those types, they are there. So you need, so there isn't, it's not custom made. With set theory, you can really make it tailor. You know, you have some clothes, you make this dress today, you make that other suit tomorrow. So it's custom made, which is a lot easier or maybe more useful to do with set theory than with type theory. Muted. You are muted.
I think he knows.
Here I am again. Okay, the interface didn't allow me to unmute. Okay, thanks a lot, and let's move to the next talk.
Cool, thank you.